yeah, so we're giving a couple minutes for people to come in, and we're just talking about grokking now. Um, do you know where the term grok comes from?
I actually don't. Do you?
I do. It's a science fiction novel, Highland, called like Stranger in a Strange Land. So
Oh,
it's a book. I kind of remember. I think it's about like an alien who lands on Earth, and like, yeah, and tries that, and Grokking's trying to understand what it's. I think it was like the alien term from the book, where he's trying to understand the world. So yeah, it's a good science fiction novel. If you happen to be in science fiction, Grokking originally comes from that.
that's super
Um,
cool. I did not know that.
yeah, it's a random fact. I think as a kid I read a lot of science fiction. So
Makes sense why you're here now in this
I-
industry, right?
yeah, totally. So those of you didn't catch that, like Grokking comes from an I think it's like a 1960s science fiction novel. Um, Generally means to understand, or trying to understand something. And I thought it was good. Like I do think. Had you read any other papers on Grokking prior, or was this kind of the first on this side?
This was my first, and I'm kind of glad it was my first because I think it really breaks down the whole kind of process of how, grokking comes to be,
Yeah,
and especially in this context for neural nets. But yeah, this was my first real paper on it.
cool, awesome. Um, we'll give it another minute here for people to come in. I thought it was a good one. Like I think this
Yeah.
whole concept of I feel like the whole concept of like generalization, which is
Mhm.
like, yeah, understanding something, understanding how to do something when you haven't seen examples for. I mean, it's you see it all over right now, and trying to understand how networks or LLMs or neural networks generalize, I think is like a fascinating, like interesting topic. Um,
Yeah.
yeah, I mean, what's generaliz like? What do you think? Like, how would you describe generalization
Yeah,
yourself?
whenever I think of generalization, I basically think of it as like the model's ability to like properly predict on something new, something like you said that hasn't been seen.
Yep.
So that's really what I think. Is like creating patterns from all of the information that it has seen and then applying
Yep.
that to when a new data point comes in.
Cool. I totally, yeah, I agree. And I think the general, like, I feel like it gets more complex. Like I found there's so many ways in which like a GPT-4 fails in some generalization in some very unique ways. So I think they kind of take a very simple approach to looking at modular addition here. Um, but I think it's kind of important for a broader set of use cases.
For sure.
Let's hop in. So um explaining Grokking. Um so when at the beginning here, it's just kind of like I think they trade off like this idea. They simplify it down to like memorization or generalization. So you can use parameters for memorization, or you can use parameters for actually learning the skill, I guess. Um and and the in terms of like I guess in terms of like the big picture, I would say like the big picture I see in this as we go through it, and like just to quickly summarize, is there's an argument made for why grokking occurs. So how does a network generalize to solve a problem? How does it move from memorization to generalization? And how does it tie to a concept of like efficiency in training, that trades off essentially parameters for parameters used, and where does it come through in kind of the loss functions and equations, and what's the arguments, and what can you use to predict that? um and the core question, I think, is like this: like, why does a network improve dramatically upon continued training, already having achieved good performance? So you achieve good performance in your training set. You're an amazing, you have amazing performance in your training set, poor performance in your test set, and at some point there's a breakthrough where your test set just improves drastically.
Yeah.
um you've learned the skill, you learn the generalization that goes beyond your training set for this. And they talk about circuits here. Do you want to describe like how you see a circuit and like what's your view of this concept of a circuit?
Yeah, I kind of just view them as like these modules that we can use for testing these hypotheses. I think like you can get into a lot of detail there and they can mean a lot of different things in different contexts, but at like a high level, that's what your circuit's going to be. It's going to be for us to actually test out these theories and the various algorithms.
Yeah, it's like if you're doing module addition, there's one way of doing module addition, there's another way of doing module addition, there's another way of doing module addition. They're all circuits and ways that the network could learn to do it. And they can all be happening in parallel with edging each other out. But it's this idea that there's a lot of ways of accomplishing the task that might be being learned at the same time. And I guess the point here is kind of one which generalizes well to, so there's kind of one which generalizes well. There's an idea of a circuit that like maybe learned how to do addition like we learned in school. And maybe there's one that's just rote memorizing data. And obviously that's going to be the one that struggles on the test set. So when there are multiple circuits, achieving strong performance, weight decay prefers circuits with high efficiency. That's kind of like the core, to be honest, like this, I think this is the core core point of the whole paper that they're trying to make, which will be, which we'll dive into deeper. And if CGen, and by C, it's the circuit that generalizes. So this is the module addition we learn, or this is the addition that we might learn in school versus CMEM, which is the, copying a table or something and just memorizing the points in the table. And I think the point here is that there's like three key properties, which is the circuit that generalizes while CMEM does not. So that's kind of like one thing, one property that they're going to demonstrate in here. Another one is the circuit generalizes is more efficient. And do you understand kind of like what they mean by efficiency? We'll dive in later, but like I think the point here is like, what's the mechanism by which gradient descent like chooses one versus the other? And the last one is just I guess the other key property is just the circuit for generalization kind of kicks in later. And then since CGen generalizes well, works for new data points. Do you want to describe this? I mean, this is like, the whole idea of generalization, but maybe just hammer it home.
Yeah. So I think with regards of like the generalization and it performing better on the new data points, I think the real thing is that like, both of these circuits can offer good training, but only that generalization one is going to be the one that performs well on the unseen data. And it's going to kind of achieve that through some level of the cross entropy loss on the training with those fewer parameters. I think those are the two key things that I think of in this. Anything else that you think of?
No, I think that's exactly it. It's like this whole concept that they came up with efficiency, which they define later on here. But the idea is like its efficiency should be independent of the training size of the data set. That should be independent of the size. That like if you generalized addition, you can do addition with like 10 numbers or 50 numbers, and it should, and you can, get a bunch of examples that you've never seen, and you should, you should be just as efficient at calculating those, meaning like you don't need to add more parameters to understand how to do that type of addition.
Yeah, I think even on that is like they noted that like if the classifier can generalize well, like it will remain consistent at any point, even when those new points. And if it can't generalize, then there's really no hope for that.
Yeah, and then I think these graphs were interesting.
Yeah.
Did you like? I think that like this one kind of tells you the first view of Grokking. Do you want to describe like what the red line is, what the orange line is, and
Yeah,
zoom here, and what's going on?
You want to zoom in there. So what we're looking at that is the grokking phenomenon that we're talking about here. And in case we didn't like explicitly say, I just think this is important. So this is just that phenomenon where the neural network is going to memorize its training data, but it's going to perform poorly on new unseen data and until it eventually learns to generalize well. And then that's like well past your additional training. So I think that's first, let's be clear on what grokking is. And that's what this is showing here, right? So when the grokking is kind of occurring, we're seeing the test accuracy, that's going to be that green dotted line. And you can see that kind of moving, it's really low in the beginning where our training loss and our test loss is, well, I'm sorry, our training loss is low and our test loss is high there. And you can see as we approach and we start reducing our training loss and our test loss, you can see at that kind of point, then our test accuracy increases. So it's kind of that trade-off. So in the beginning portion there, we're kind of in that memorization phase. We're doing really well on our test data. On our training data, but we're not doing well on our test data. And as we continue to train, if you follow that kind of that red line, well past maybe that point of where we think that we're doing well on our test set, on our training set, then it's going to kick up. And then we're going to see that improved test accuracy, which is where that grokking is actually happening. So that point where you see the loss kind of decrease and the test accuracy increase, that's kind of where we're seeing that grokking happening. And we'll get a little bit more, I think, later on to how the data set and all of the other parameters play into that.
And this, I feel like the ungrokking was one of the more interesting things in the paper too, which is it's a little bit different, I guess, than what you hear. There's another industry term called catastrophically forgetting. Yep. In this case, though, they train on a smaller data set and show that you can actually go back to where you were in terms of your test loss. So I think this is interesting. This is like what I don't think I've seen this anywhere else yet, but I thought this is interesting where they dive into this, which just helps. I feel like what was pretty useful about the papers, they like actually predicted this and it did what it did by their theory. And I think this is, efficiency should decrease as training size increase. We talked about that. There's a crossover point. So you kind of see it up here. They talk about like your critical data size. I think that was another interesting thing from this paper, like the whole idea that with enough data, you can generalize. I mean, that's another kind of subtle point, like throw enough data at it and you can generalize, which seems to imply like more data is better. But I thought that was kind of an interesting thing that came from this theory. I guess we kind of know that, but it comes from the paper here.
Yeah, I like that the evidence of it all really is kind of, like you said, we kind of know that in theory, but here it's really showing you like what that point is and where that trade-off between memorization and generalization is in relationship to that data size.
Yep. And so in ungrokking, we talked about this. It's trained on they first get it to grok and then they go and train some more on a smaller data set and get it to ungrok. So like, I think it's a really good, you'll go through here, but it's a really good case for their theory, at least on the small example they have actually being correct. And then the semi-grokking, it felt a little, it's an interesting phenomenon. They describe it. It seems that it's kind of like when you're on the borderline of the critical data set, what happens? We'll dive in deeper, but I definitely seemed like ungrokking was easier to figure out what that critical data set size was, where semi-grokking was a bit harder. And it's kind of what the contributions they make here. So demonstrate, really the ideas behind this. They go through the basics. A classifier here, the core idea is that I think one of the core ideas is that there's a probability here, and that probability is the logit, the logit size, the size of the logit, and there's some relation to the number of parameters needed for that same probability. So that's one of the big ideas, I guess, in this. Anything else you'd add to that?
Not really in this section. I think as we scroll down and we take a look at that loss there is just kind of really highlights the balance. I think that for me, the other stuff is kind of more straightforward, but I think this is super important here, right? So we have the cross entropy loss drives the classifier lodges to increase in size, and then the weight decay works to reduce the model's parameters. So we really need to balance those two things because they're kind of opposing forces. So I think that was the main things from this notation that I was like, okay, we got to remember that as we move on.
Yeah, exactly. And I think the subtle point in this is that there's one side here that probably is favoring CMEM, which is like, let's just increase parameters and increase logits. And there's another side that's favoring the C generalization, which is the weight decay side of this. And the weight decay is just trying to, smallest parameters as possible. And so kind of there's this balance and trade-off between the two. And there's an argument that, the argument they make, I think pretty solidly is the weight decay is actually what's responsible for the generalization. And so there's kind of trade-offs between, cross entropy and weight decay here. The defined circuits, which we talked already about, it's just the different ways you can get at your task, and then the other thing we talked about, given multiple algorithm, given an algorithm, there's actually multiple circuits that there's many ways in which you can actually solve, including memorization. So, and this kind of hits that first point, which is like the first term is kind of driven by gradient descent and scaling up the classifier's logits to make it more confident. So it's like that first term is kind of incentivizing more parameters, where the weight decay is kind of pushing you the other direction, so decreasing the parameters. And then you can think of I also think of parameters as memorization, like you're going to need more parameters to memorize. So by this push to do it with less parameters means you can't memorize as much. So it's kind of like those two opposing forces that they're arguing here.
For sure.
And then there's some, I don't know, any thoughts on this one? I don't, when we have multiple circuits achieving strong accuracy, constraints apply to each individually. It's just like the multiple circuits working together at the same. I mean, maybe it's kind of hinting at the semi-grokking, what happens in that phenomenon where you have, lots of stuff going on and things opposing each other, balanced by each other at about the same rate.
Yeah, I just thought this was kind of interesting too. How they talk through the intuition, right? They're saying that, okay, intuitively the answer depends on the efficiency of each circuit, that is to the extent which each circuit can convert relatively small parameters into relatively large logics. So I think that's kind of, it ties back to that push and pull again, but I really appreciated the way that they broke this section down for me. When you're reading any of these papers that are kind of heavy on the logic, I felt okay, I'm following with them at this point. Okay, that does make sense.
And I think I highlighted this one even deeper because I think it's the core of the idea. There's this idea of efficiency, and efficiency is less parameters for the same logit or probability. Less parameters, same logit probability, and the more efficient circuit kind of wins in the end. I mean, that's kind of what their point is. So let's see, first phase element, CMEM, learn quickly. Yeah, and there's kind of a first phase. I mean, they also argue there's a first phase, CMEM is learn quickly. I'm not sure why. I mean, maybe it's the weight. I'm not sure why it's, I guess it's faster, it's easier. There's no decay on the, decay term on it. You can just, quickly gradient descent to the parameters that are memorizing the circuit. Maybe it's just, it's faster and easier to do that. And then it's exactly that. The second phase is where the parameter norm, that second term is reallocating the efficiency from reallocating the parameters from CMEM to CGen. I guess one question, I don't know if I thought this was answered. I mean, do you think there's really a reallocation, or does just one term beat it, or does parameter norm, because there's a parameter norm term, you're going to be shrinking the CMM parameters at the same time increasing, the circuits that have the generalization ability.
Yeah, I have the same kind of pause there of like, what are we actually like reallocating? And I think it's just kind of that trade-off that they're talking about here is like, it's just kind of what's like naturally occurring, like as we like approach so the CMEM is going to happen a lot quicker. And like, as we approach that point, it's kind of going to switch over then to where the CGen becomes more efficient there. So I didn't really see it as like a literal reallocation, but that was my interpretation as well.
Totally. And it says the overall explanation relies on kind of 3 ingredients. I think we've talked about generalization a lot. We've talked about efficiency as well. The slow versus fast learning. I guess the point there is that like there's some transition point where this kind of moves from one to the other. I think these are the three core ones, and we've kind of talked about these three properties. And then what they do is like they construct a really simple example. I think it goes through here, but it's actually a modulo addition example that both is set up with a training set that pushes memorization. There's one that pushes that helps also test the generalization. So it's like a really simple handcrafted single algorithm experiment, which the other question is like whether that's going to generalize, no pun intended, to other types of circuits. And so like, and their point here is kind of, they're just describing a little of that, like they've hard coded these tables, and this is how they're doing the testing. So generalization, and a little bit of how they set up the test environment to do this. So it's just a little bit of the simple test they put together. I actually thought it was a pretty, believable, like I came away going like, I think this does explain quite a lot. And kind of, I picked up a lot from it. Incorrect predictions on the test data set. So
I thought it was interesting too that they made all these assumptions, and the design choices were really designed to be like simple and tried to be analytical and traceable, rather than reflecting like real life examples of this in practice, which I thought was interesting. Because I think for me, if they had jumped right into like grokking in practice, I probably would have been lost. But since they did this approach, I thought it was easy to grok what they were saying.
Oh, agree. And so there's there's a data set. So they talk about a classifier here for on the memorization and the test set. What my takeaway here was they're trying to model the learning. I didn't read the paper behind this where they split these out, but they're trying to model the learning process on the data sets. And there's some challenges to being able to do that. So it looks like you need to split out split these out into subweights to be able to model this correctly is what's kind of my take. This one was interesting, but I didn't feel like I had the background I feel like I need to go back to the previous paper to understand a little bit of like the reason they're splitting this out and the challenges of it. And then above, it says, about efficiency, we operationalize circuit efficiency as the extent to which the circuit can convert relatively small parameters into large logits. Same in efficiency determined slowly by parameter norm. So when the weights are all one, each circuit produces a one-hot vector as is logit. So the logits are scaled. So like basically I guess it's the largest probability, and then it's the same thing, like the parameter the parameter norm of the generative circuit should be less than the memorization. So it leaves a question of like how to model the parameter norm when weights are not all one. So they kind of intuitively increasing weights corresponds to increasing parameters in a neural network, so the scale up resulting outputs. So that they have come up some other way here that they represent like how to look at kind of efficiency when you're and how really to model the parameter norm for this case where you're not all ones and coming in from and it's not like a single one logic. Any other additions for these sections here? Theoretical analysis, we first analyze optimal solutions to the setup above.
Yeah, I feel like for these sections here, for me, it really just was like laying the groundwork of like what assumptions were made, what was the setup process they used, so that you have that clear understanding when we get into the next section. Okay, like what are the phases, if you will, that need to take place for grokking to come up, and what assumptions they made to contribute to that. That was really my takeaway from that section.
Yep. And then I think these, so in this section here, so in this section here, why generalized circuits are more efficient. So this kind of talks about like why why CGen is more efficient and its relationship with data set size. I think this is probably, I don't know, one of the more interesting actionable things. I mean, the fact that they did find relationships between data sets, the relationship, I think, between data set size and actually the grokking in this was actually some of the more interesting findings, in addition to like the ungrokking. So their point here is like, if you add an additional point as you add additional points, that the generalization circuit should be more efficient, shouldn't need more parameters, meaning efficient meaning parameters to understand it, to keep that loss low, where the one that's memorizing is going to need more parameters as you add more data.
Yeah. It's kind of interesting too to me here, because it kind of seems like the perspective here, and when we get to this section, it's kind of focusing on the generalization aspect, like kind of making the assertion of, okay, if the classifier can generalize well, then it will remain, that its efficiency will remain constant. But if it fails to generalize, which kind of made me feel like, okay, so now we're talking about the memorization piece, that it will just struggle. But it's kind of interesting that they focus more on the generalization lens in this section.
Yep. Yep. So now it's supposed HD instead fails to predict. So this is kind of talking about like what happens with the memorization one. Applying analysis circuits. So we should expect see.
I thought this was.
Yeah, I thought this was a good point.
Yeah, like just basically saying, or this was my takeaway, at least the note I wrote on my side was that the generation circuit is able to maintain efficiency because it doesn't need to significantly change those parameters to adapt. Whereas for the circuit that's memorization, it has to adjust those parameters for each new data point, and that's where it's really losing that efficiency. And that for me, like really kind of drove that point home for me.
And then this is probably the most important thing that like I get, I think it's the biggest challenge out there. Like, how much data do you need? And like, and obviously there's going to be many circuits for say a GPT-4, right? Like there's so many things it's learning. But what's the right data size, and what's the critical data sizes that you need to actually generalize? And is it, I mean, it's an interesting point too here, where it's kind of like more data, not more training. I think that's a very subtle point that what's needed in this case is more data to generalize, not necessarily the more training. So maybe there's some big idea out there in the LN space on this. So decrit so the data critical point at which is their point is like, it's kind of where they're equally efficient from a circuit perspective. So I think that's kind of the core idea, is that the transition points where those loss functions, those two parameters and loss functions, are trading off against each other. And then there's the effect of weight decay. I thought this was kind of like their other big point, that like it's based upon data size, not a function of like weight decay itself, that the weight decay maybe determines where in training it happens, but not necessarily if it happens, or the strength of it. Yeah, so that's the point. Like it may affect that, like when it happens, not if. Ungrokking, which seems to be a good way of, I mean, it's an interesting way of, I mean, that might be something that people end up using, like to understand. I mean, I think this is a fascinating idea. Like unlearning skills might help you tell what's your critical data set size. I thought that was kind of like another fascinating thing here. Maybe there's some use for that.
Yeah, I thought that, and also like kind of something to be cautious about too, as well. Like as you approach, like if you have your model is grokking and then you try to, you know, do some additional training with a smaller set, like beware of this phenomena that might occur. You'll see that performance go down as a result.
Yeah, it's kind of like, you know, be wary of too much fine tuning, I guess, maybe here too. Like can you break skills by fine tuning and on some weird smaller data set? I think you see it a lot too in some of the LM stuff, where the people mix in the training set with the fine tuning set. So like they might randomly mix in, you know, for large fine tunes, but yeah, so there's something kind of here as well.
That's kind of exactly my thoughts when I read this. I was like, I wonder how this relates to the fine tuning in LLMs, because, you know, you have this extremely large data set, right, that we're doing our pre-training with. And if we fine tune on too small, is that why we, you know, we don't see the performance improvement that we would think with fine tuning for LLMs? Because, you know, for a while it was like, oh, you only need 100 data points to fine tune, right? Like maybe that's just like way too small. So that definitely got me thinking when I read this part.
Yeah, and I think the good news is, normally, you know, the fine tune approaches, you're freezing, like an LLM, you're typically freezing the weights, maybe doing lower or something like that. So you're probably not like causing this problem. But it's worth, and you're probably not fine tuning a ton. Like it might take 1,000, 10,000 samples. People aren't doing as much as, you know, it's worth noting, but yeah, I'm not quite sure it's going, you know, that breakage is going to totally occur in those situations. Ungrokking can be seen as a special case of catastrophic forgetting. So this is kind of like that hint that you're hearing this out there in the ecosystem. What do you think catastrophic forgetting is? What's that to you, SallyAnn?
Sure. Yeah. So I honestly haven't read the paper there that it's mentioning, but when I just like kind of looking at it, of where just the model kind of just starts forgetting like some of the information that it's been trained on, things that it's referenced before, and it just causes like this total degrading of performance. That's kind of what I think of it as.
Yeah, if you and those of you who've been out there, there's a recent paper on like reversal symmetry, A versus B, and it's like the parents of Tom, you know, Tom Cruise's parents are this, and you know, he's the son, you know, it's kind of taking a bunch of examples where someone's the parent or son of, and see if it knows the other relationship. And they gave some examples of fine tuning where you can it knew something, it knew that relationship, and then you train it on some data and like breaks the thing it knows. So that's kind of the way I see it, is that you know something, and then you're breaking what you know by some fine-tuning exercise. And I think their point is kind of like, it feels like this is related to that. Semi-grokking, you know, again, that probably wasn't the thing I thought was the most interesting here. Interesting phenomenon, but you know, not as probably useful. They talked about kind of different evidence out there for why this is occurring. Talk about their experimental setup. Okay, so you know, I thought this was kind of like the core view.
Yeah.
So so you've got your logits, you've got your colors by data set size, and a very clear, you know, pattern of parameter norm increasing by data set size, where for a fixed logit. And then down here it's all mixed in, like, you know, you know, you can do larger data, get the same logit or probability of output, but with a smaller set of parameters. It's kind of the core.
Yeah, I thought that made it really, really clear.
Yep. And then we've got efficiency of CMEM. So CMEM requires log. I mean, again, same ideas, same concepts here. However, norm is required to do is increase the applying efficiency. Again, just showing the results kind of match, those graphs and results match. Yeah, so I thought this was good. This was an interesting one with this, the ungrokking at different data set sizes. So this is, you know, as you run with smaller data sets here, you can get like poor test accuracy versus, you know, the larger. I mean, it just shows very clearly. And then I think their point was like, with different weight decays, they all collapse on top of each other here.
Mhm.
So it's like kind of independent of weight decay was kind of, I think, one of the points they were saying.
Yep.
Phase transitions for plot accuracy on yeah, it's kind of about where it comes, and then this is the point of the weight decay. And semi-grokking, let's skip over that. Yeah, and this is the point, like if you really want to know your critical data set size, the ungrokking might be the better thing to use. It's much more clear from a transition period. Yeah, and they talk about related work. So what is grokking, how it's related to weight decay, you know, a pretty good discussion here of kind of like the generalization, like is weight decay require, like weight decay, you know, is the kind of that shrinking of parameters, that's the thing that's supposed to push the generalization. But I think their point is like there are some examples of grokking occurring in places where there isn't weight decay, but it doesn't mean that their explanation is not correct. I think that's what I kind of came to the same conclusion. Just because you can get grokking outside of this doesn't mean this isn't what's happening. However, in realistic settings, good training achieved model has very different circuit families. Yeah, so I think this is kind of, you know, the final thing, which is like the different open questions they have within grokking here. And if people have any questions for the authors or want to leave them, the authors actually offered to answer any questions. So if you all have questions that you want to put to the authors or talk to the authors about, and I think these are, you know, I think one of the biggest ones is like, it's still open to me is I mean, generalization is so important. You know, get these skills that come out and all of a sudden you get them, and like predicting generalization, understanding generalization, like how to, like, you know, this was a very simple example with modular addition. Like what can you say about like data set size versus generalization versus fine? Like, I feel like there's a bunch of open questions in addition to the one we brought up on fine tuning. Yeah, so those are kind of the ones I have open for myself.
Yeah, I definitely agree with the data set size. I was just even curious about, you know, like the estimation of that critical data size and how it was initially estimated. So interested in that. And then I was also curious about the loss function that they chose to go with and if they considered any other. So I'm looking forward to getting some answers on that.
Cool. Awesome. Well, thank you everyone for joining us on grokking, and we'll see you next time. Awesome. Bye.
Bye.